Welcome back everyone. In this lecture we will see the second isomorphism theorem. So let us begin with recalling what we proved in the earlier class, that is the first isomorphism theorem. So, here is the recap. So this is called first isomorphism theorem. So this is somewhat most fundamental result in isomorphism theorems. So suppose if we have a surjective function, let us state it this way. So phi is a group homomorphism which is also onto. So phi is group homomorphism. So then we have this kernel and image which is G dash. Okay. So the kernel of phi, so which is those x in G such that which is mapped to identity element inside G dash. So then you can actually formulate this quotient group. Okay, you have diagram like this. You have from G to G dash, you have phi, and then you have this natural quotient G modulo kernel phi. So this is again surjection. Okay, so let me denote it by the quotient phi. Sorry, the quotient, let's call it pi. So this is the quotient map. So then what we proved indeed, we proved that there exists a map from this G modulo kernel phi, okay, which we called it as phi tilde, okay, such that this is an isomorphism. So if you talk in terms of diagrammatic language, so we say that this diagram indeed commutes, and not only that, this phi tilde is indeed isomorphism, that is part of the theorem. Okay. So what is the meaning of this diagram commuting? Okay, let's rewrite here. So G to G dash, you have a map, and then you have this quotient map from G to G modulo kernel phi. So then you have this induced map phi tilde. So just saying this phi tilde is induced from this phi, so that is the same as saying that this diagram commutes. So that means if you take an element inside G, okay, so let's take some element x in G and then look at its image under phi. So that will be element here inside G dash. Okay, so then obtaining this image phi x, okay, so you have other way to obtain this. Okay, you can go down from G to G modulo kernel phi. So there you will be mapping to pi of x, and then this pi of x will be mapped to some element under phi tilde. Okay, so there will be phi tilde of pi of x. So we expect that that is same as this pi of x. So that is the meaning of this diagram commuting. Basically this phi tilde is induced map from phi, that is what it means. Okay. So in a more precise way, using the definition, you can see that if you actually look at the image of some given element x in G, there are two ways to look at the image. One is straight away look at the image under the map phi. So that is mapped to phi of x. So then you go to this x to the image of that x under pi, and then take phi tilde. So that element should be same as phi of x. Okay. So note that what is phi of x, that is by definition x into kernel phi, and if you recall, the phi tilde of x kernel phi is defined to be phi of x. Okay. So that is why this diagram is commuting. But the statement of the first isomorphism theorem indeed says this phi tilde is indeed isomorphism from G to G dash. So is on isomorphism. So the way I stated the map phi tilde, phi tilde is from G modulo kernel phi. So I stated it as G modulo kernel phi to the image of phi, but here I have assumed to begin with the map is onto, so the image is G dash. So one can rewrite the first isomorphism theorem as this. Okay, no issue. And we have seen various applications of this first isomorphism theorem. Okay, so now we will prove the second isomorphism theorem as another application of this first isomorphism theorem. Okay, so what is this second isomorphism theorem about? Okay, so that is about understanding something about subgroups and normalizers. Okay. So let me just state the theorem. Okay, before that let me just tell you what are all the things that are involved in the second isomorphism theorem and how to remember that. Okay, this is also called diamond isomorphism theorem. So why that name comes? So once I draw the picture, it will become clear. So basically, the second isomorphism theorem involves, let's say, two subgroups, call it capital A, capital B. So G is given group and capital A and capital B, they are given subgroups. So now you assume that this A is indeed subgroup of the normalizer of B. Okay. So I will tell you in a minute why this condition is very important. Okay. So basically we are looking at these two groups. Okay. So let me draw this diagram. So you have A, you have B, so you have G sitting on the top. Okay. So naturally you have this set AB that is there in between this A and B. Okay. A is contained in AB and as well as B is contained in AB. Okay, that is all I am saying. So note that A is contained in AB, B is contained in AB. Okay. What is AB? Recall AB is nothing but all those products small a, small b, where A is coming from capital A, B is coming from capital B. Okay. So now, so a priori this AB, okay, need not be subgroup inside G, okay, but it will be nice if it is a subgroup. Okay. In that situation, we can actually connect these things with the following things. Okay. So you have this another group which is lying at the bottom. Okay. So that is contained in this A intersection B. So I am putting this line segment, okay, whenever the inclusion happens. Okay. A intersection B is contained in B, A intersection B is also contained in capital A, and similarly capital A, capital B both are contained in AB and AB is contained in G. So now I want this AB to be actually subgroup, okay, and one can note that under this assumption, okay, when A is contained in the normalizer of B, so then this AB becomes naturally BA. So in that case AB becomes subgroup. Okay, that is why we need this condition A being subgroup of the normalizer of B. So in that case we will prove that, okay, this A intersection B will become naturally normal subgroup of A and B will become naturally normal subgroup of AB. Okay. So then we want to compare what happens with AB modulo B and A modulo A intersection B. Okay. And indeed the second isomorphism theorem tells you that these two are isomorphic. So this is the statement of second isomorphism theorem. Okay. Okay, so let's try to actually properly prove all these things. Okay, before stating the proper second isomorphism theorem, let me just prove this proportion which I actually promised, because under this condition I told this AB becomes a group. Okay, that is the first thing to verify. So there are so many facts that are there to verify. Okay, let me state it here. So for example, so AB is a group, okay, subgroup. So that is one thing, and then B is normal in AB. That is the second statement. The third statement is A intersection B is normal in A. So all these things we want to actually verify. Okay, so then only we can talk about the respective quotients AB modulo B and then A modulo A intersection B. So let's verify one by one under this condition. A is being subgroup of normalizer of B. Okay, so the first statement, okay, assume, okay, let AB are subgroups of G such that A is contained in normalizer of B. We already verified normalizer of a subgroup is a subgroup. So in particularly A will be a subgroup of normalizer of B. Okay. So then, so this is proportion. What we want to claim? We want to claim that AB is equal to BA. In particular, AB is a subgroup of G. The second thing is B is normal in AB. Third thing is A intersection B is normal subgroup of A. Okay. So to remember this statement, remember this diamond diagram. Okay, this looks like a diamond. Na? So this looks like a diamond, and all we are saying that this double lines indicates which one is normal in which. Okay. So just a pictorial interpretation to remember this statement. Okay, so let's verify one by one and then see. So first statement, AB is equal to BA. So we already proved AB is being equal to BA is same as equivalent to AB being a subgroup. Okay, that is something we verified earlier. So let's use that. So now if you want to verify AB equal to BA, let's recall the normalizer definition. The normalizer of B is those G in capital G such that G normalizes this B. So that means the conjugate of capital B under G is same as B. So that is the definition. So now it's given that A is subset of Ng of B. So in particularly, if I take some element small a capital B A inverse, okay, for any small a in capital A. So we have, because A is element of the normalizer, AB A inverse will be exactly equal to B. So what does that mean? That means AB is same as BA. So the left coset is same as right coset corresponding to this A. So that means what? That means if I take this A B, which is union of small a B, A in capital A. So this will be exactly equal to union of B A in capital A. Okay. So if you just think about it, this is exactly B capital A. Okay. So that proves that AB must be a subgroup. So the first statement is verified. Now look at B. Okay. So note that B is obviously subset of AB, because you can write any element B in capital B as identity times B, so which is in capital AB. Okay. Similarly, A is also subset of AB. Okay. Now we want to say that B is indeed normal. Okay. So what we need to verify for that? If you want to say B is normal in AB, so this is our claim. So take some x inside AB. So then look at x B x inverse. So it is enough to prove one of the characterization says this x B x inverse is just a subset of B. So this is enough. But given x, there will be some small a, some small b. such that x equal to AB, okay, for some capital A in capital A and B in capital B. Okay. So, this is what we need to check. So, how do we check this? So, let us see. So, let us blindly compute x B x inverse is equal to A B capital B A B inverse. So, what it is? It is A B capital B B inverse times A inverse. Okay. But what is B capital B B inverse? Since B is in, okay, B is in capital B, B capital B B inverse is going to be exactly B, because B is a subgroup, okay, as B is a subgroup of G. So, this is something you can check, there is no issue. So, now in particularly if you apply the conjugation of A for this B inverse, then what do you get? You get exactly A B A inverse. Okay. But what is A? A capital A is actually coming from the normalizer of B. That means A B A inverse is capital B. So, that says that this is exactly equal to capital B. Okay. So, that proves indeed we checked actually this is equal. So, that proves that for any element x in capital AB, okay, if you conjugate B by that x, then you get B. So, that means B is normal in capital AB. So, this proves that B is normal in capital AB. So, in particularly we can talk about the quotient, okay, we can talk about AB modulo B. Okay. So, let us look at what will be the quotient. Okay. So, the AB modulo B, how it looks like. So, by definition this is going to be x B x in AB. So, this is by definition, but how the given x in AB looks like. Okay. Any x looks like some small a b, where A comes from capital A, B comes from capital B. So, then x capital B will be A B capital B, but A B capital B is same as A times B capital B, but now B is coming from, small b is coming from capital B, that means B capital B will be capital B only. So, then this is exactly A capital B, as B is a subgroup of G and B is coming from capital B. So, B capital B equal to capital B. Okay. So, that means anything that you take, any coset corresponding to this capital B, okay, x B, that is going to be represented by element of capital A only. So, then this can be reparameterized as A capital B, A coming from capital E. Okay. So, this is already one such parameterization. But now we want to really understand what it is as a group. Okay. Can we relate this with something else? So, here you see already all the elements are already represented by elements of capital A. Okay. But it can so happen that if A B may be equal to A dash B. Okay. So, in that case what will happen? A inverse A dash is going to be element of B. So, two cosets can be equal, okay, that can happen. When it will happen? It will happen if and only if A inverse A dash should be in capital B. But what is the meaning of this? This implies immediately A inverse A dash. Okay. So, this is first of all element of capital A, because both A dash they are coming from capital A, and then A dash and capital A is a subgroup. So, A inverse A dash that should be in capital A, but it is already in B. So, that means it is in the intersection. So, that means, so this thing A B equal to A dash B, that is characterized by A inverse A dash is being in capital B, which is again, if you think about it, characterized by A inverse A dash is being in A intersection B, because A dash both come from capital A. So, that implies immediately, if you look at A intersection B, this coset is same as A dash A intersection B. So, in a way you are relating these two cosets being equal same as these two cosets being equal. Okay? That is what motivates us to actually look at A modulo A intersection B, because two elements in this quotient being equal same as saying that two elements equal in A modulo A intersection B. Okay? So, what we indeed proved? We proved that if you take two element x, okay, let me just write it using A only. If you take A B, A dash B, two elements in A B modulo B, then A B being equal to A dash B. Okay, let us now write it this way. For A dash in capital A, we have A B equal to A dash B inside A B modulo B, if and only if we proved A, the coset corresponding to A intersection B is same as A dash A intersection B in A modulo A intersection B. Note that A intersection B is a subgroup of capital A. So, A modulo A intersection B makes sense, left cosets make sense, there is no issue. Whether it is a group or not, that is something we need to check. To check that, we need to check A intersection B whether it is a normal subgroup or not. Okay? If it is a normal subgroup, then this suggests that both must be isomorphic. Okay? So, let us see why A intersection B is indeed normal in A. So, to check that, start with x in capital A and then look at x A intersection B x inverse. Okay. So, we need to prove that x A intersection B x inverse is indeed subset of A intersection B. So, this is what we need to check. Okay. So, why this is the case? Start with some z inside A intersection B. So, then look at x z x inverse. Okay. So, now this x is coming from capital A, z is coming from again capital A. So, the conjugation x z x inverse will be naturally in capital A as x and z both are elements of capital A. Okay. So, this is fine, no issue. So, now what is about x z x inverse being in B? Note that z is coming from B and A is subset of the normalizer. So, that forces that this element should be in B, as z is coming from B and A is x is in A, which is in the normalizer of B. So, this is again by definition. Okay. So, that means this element x z x inverse is in both A and B, it is in the intersection. So, that is what we need to check. Okay. So, which is checked, that proves that. So, this implies this argument A intersection B is normal in capital A. Okay. That means A modulo A intersection B makes sense. So, now how to prove that indeed we have this isomorphism? Okay. So, for that we need to construct this map. Okay. Let us construct the map and then of course, need to use the first isomorphism theorem to conclude anything about the quotients. Okay. So, what is the natural map? So, you can take this projection, okay, take AB and then look at this AB modulo B. So, this is a quotient map. Okay. So, this is, let us call it pi. So, this is the natural quotient map, take x and then send it to xb. So, this is something makes sense because B is verified to be normal inside AB. So, AB modulo B makes sense, and this map is a group homomorphism. Okay. This is a group homomorphism and this is surjective group homomorphism. Now, what we can do, we can restrict this map to capital A. Okay, because A is being a subgroup of AB, we can restrict this map to capital A. So, then we get a map from A to AB modulo B. So, this is again a group homomorphism because restriction of a group homomorphism is a group homomorphism. So, that is something we verified. Okay. So, now if you take this map, what it is actually sending, okay, let us call this F of small a is nothing but A capital. Note that using our parameterization, so we already have this parameterization. Okay. So, this says that each element of this AB modulo B parameterized using elements of capital A, okay, A, B, A and capital A. So, that means this F is already surjective map. Okay. So, F is surjective. So, that is not a problem. So, immediate. Okay. So, we need to define, and this is well defined map, that is clear because it is just a restriction map. Now, we need to verify whether it is a group homomorphism or not. Okay. Let's check that. So, let us check F is a group homomorphism. Then what we need to check, F of A1 A2 should be same as F of A1 times F of A2. But what is F of A1? That is A1 B. F of A2 is A2 B. So, F of A1 times F of A2 is A1 B times A2 B. But note that we are in the group, okay, B inside AB, B is normal in AB. So, that tells you that this is exactly same as A1 A2 B. Okay. This is F of A1 times F of A2. But what is F of A1 A2? So, that is exactly by definition A1 A2B. So, these two are equal now. So, it is basically, this is just a, okay, this is a restriction of a group homomorphism. So, I unnecessarily verified it is a group homomorphism. So, it is immediate that F is also group homomorphism, surjective group homomorphism. Okay, two things are verified. So, now using this first isomorphism theorem, you can see that A modulo kernel F will be isomorphic to AB modulo B. So, it is enough to determine what is the kernel. The kernel is nothing but those A in capital A such that F of A equal to identity, where identity inside AB modulo B. Okay. So, let us rewrite that. This is those A in capital A such that what is F of A? That is AB. What is identity in AB modulo B? That is just B. Okay. So, if you just see this, this tells you that AB equal to B if and only if A is in B. Okay. That is easy to verify. I will leave it to you to verify. So, then from this you can see that kernel F is those A in A such that A is in B, which is nothing but A intersection B. So, indeed we proved that A modulo A intersection B is isomorphic to AB modulo B. So, this is something very powerful. Okay. In theoretically speaking, it is a very useful result. Whenever you have two subgroups, they behave nicely. okay, that is A is contained in the normalizer of B, then you are able to take the product of those two subgroups, which will be again a subgroup, okay, and then if you take AB modulo B, then that will be naturally isomorphic to A modulo A intersection B, okay. So, from theoretical point of view, it is very useful result. So, later when you study like more advanced finite group theory course, in the classification of finite groups, these things will be very used very much. Okay, so I will stop here, and then I will continue with third isomorphism theorem and some applications of this isomorphism theorem in the next class. Thank you. I will stop here.